It's long been believed that the universe began with a powerful flash, around 13.8 billion years ago. Space, time, and matter all emerged from nothing. But what if that nothing wasn't empty? What if the true origin lies behind the veil, in a realm where the laws of physics unravel and reality itself dissolves? Science hesitates here. General relativity collapses. Quantum mechanics stutters. Yet, bold minds persist, peering into the abyss of the quantum fog, a chaotic, pre-temporal ocean where space and time have no meaning and only potential exists. Could our universe have sparked from a flicker of nothingness, bounced from a dying cosmos, or emerged from deeper dimensions still hidden from view? Each theory whispers a possibility, a glimpse into the unthinkable. This documentary dares to ask the forbidden question, to cross into the unknown, to explore what came before the beginning.
At the smallest scales, space breaks into tiny loops and time into slivers. This is called quantum foam. Here, space-time becomes fluid, a restless field where tiny parts of the universe appear and disappear.
It is here, at the Planck scale, that the seeds of our cosmos may have formed, not through a single explosive event, but as a subtle shift within a turbulent, probabilistic landscape. Quantum foam arises from the principles of quantum mechanics, specifically the Heisenberg uncertainty principle, which states that energy and matter cannot be precisely defined at tiny scales. At the Planck scale, this uncertainty manifests as rapid fluctuations, producing virtual particles and antiparticles that emerge and vanish almost instantly. These are not random quirks, but a fundamental feature of reality, creating a dynamic, frothy structure where space-time itself is no longer smooth. First described by physicist John Wheeler in the year 1955, quantum foam is envisioned as a chaotic tapestry of microscopic wormholes, transient black holes, and bubbles of geometry that form and dissolve in a ceaseless dance. Imagine space-time not as a fixed grid, but as a bubbling broth, where each bubble represents a fleeting configuration of energy and geometry. Most of these configurations are ephemeral, collapsing as quickly as they appear. Yet, within this turmoil, a rare fluctuation could stabilize, expanding into a structure capable of growing into a universe. This process, called quantum nucleation, suggests that our cosmos began as one such bubble, a momentary alignment of quantum fields that sparked the rapid expansion of the Big Bang. At the Planck scale, classical physics falters. General relativity, which describes gravity as the smooth curvature of space-time, cannot account for the quantum effects that dominate here. Instead, space-time becomes quantized, broken into discrete, fluctuating packets. Quantum field theory, which explains particles and forces as vibrations in underlying fields, reveals that these fields are in a state of extreme agitation within the foam. This agitation produces not just particles, but entire geometries, creating a landscape where space-time itself is reshaped moment by moment. Central to the foam's behavior are virtual particles, born from borrowed energy as allowed by the uncertainty principle. These particles generate transient structures, wormholes linking distant points, black holes that evaporate in an instant, and bubbles of space-time that may expand or collapse. In some scenarios, a bubble driven by a field known as the inflaton underwent rapid expansion during cosmic inflation, smoothing out the foam's chaos and laying the foundation for the universe's large-scale structure. This inflationary phase stretched quantum fluctuations into the seeds of galaxies, leaving faint imprints we can still detect today. The energy density at the Planck scale is immense, making gravity itself a quantum phenomenon. Space-time bends and twists under these extreme conditions, forming a patchwork of geometries rather than a continuous fabric. Models like causal dynamical triangulation propose that space-time at this scale is built from tiny interconnected simplices, geometric units that self-organize into a four-dimensional structure. In this view, the quantum foam is a network of possibilities, a dynamic framework where the universe's geometry takes shape. Zero-point energy, the baseline energy present even in a vacuum, drives the foam's fluctuations. This energy creates a landscape where every possible arrangement of matter and spacetime is briefly tested. A fluctuation with the right properties, perhaps a specific energy configuration, could have triggered the exponential growth that became the Big Bang. Inflationary cosmology supports this idea, suggesting that the universe expanded rapidly from a microscopic seed, transforming a quantum event into a vast, uniform cosmos. Directly observing quantum foam is beyond our current capabilities, as the Planck scale lies far below the energies probed by particle accelerators like the Large Hadron Collider. Yet, indirect evidence persists. The cosmic microwave background, a snapshot of the universe's early light, contains patterns of temperature variations that trace back to quantum fluctuations stretched by inflation. These patterns are like echoes of the foam's activity, preserved in the sky as a record of the universe's infancy. Theoretical frameworks offer further clarity. Quantum field theory predicts that the foam is a natural outcome of combining quantum mechanics with gravity. String theory, which describes particles as tiny vibrating strings, suggests that the foam may involve extra dimensions, curled up at Planck scales, adding layers to its complexity. These models portray the Big Bang not as a singular beginning, but as a transition where a stable fluctuation emerged from a sea of possibilities to form our cosmos. The quantum foam is a realm where the distinctions between space, time, and matter blur. In the quest to understand the origins of the universe, we encounter a realm where the very concepts of time and space dissolve, a timeless, spaceless state that defies our everyday experience. This is not a void in the classical sense, nor a place where events unfold in sequence. Instead, it is a condition where the frameworks of general relativity and quantum mechanics, which govern our reality, cease to function. Here, the question of what existence means takes on a profound new dimension as the familiar scaffolding of reality unravels. The timeless state emerges from the limitations of our physical theories. General relativity, which describes gravity as the curvature of spacetime, predicts that at the Big Bang, spacetime collapses into a singularity, a point of infinite density where time and space cease to exist. At this extreme, the equations of relativity break down, unable to describe what happens. Quantum mechanics, which governs the subatomic world, also falters in these conditions, as its probabilistic nature struggles to define a reality without a temporal or spatial framework. In this pre-cosmic state, the universe exists in a form that lacks the dimensions we take for granted. To conceptualize this, consider a realm where there is no when or where. Without time, there is no sequence of events, no before or after. Without space, there is no distance, no separation between points. This is not emptiness, but a state of pure potential, where the distinctions between past, present, and future, or here and there, are meaningless. Some physicists propose that this timeless, spaceless condition is governed by a proto-reality, a substrate of quantum fields or abstract mathematical structures that precede the emergence of space-time. One approach to understanding this state comes from quantum cosmology, which attempts to merge quantum mechanics with gravity. In this framework, the universe at its earliest moments is described by a wave function, a mathematical entity that encodes all possible configurations of reality. Unlike classical physics, where a universe has a definite state, the quantum wave function represents a superposition of possibilities, none of which are fixed until they collapse into a specific outcome. In the timeless state, this wave function exists without a temporal or spatial context, a probability cloud of potential universes waiting to take form. The Wheeler-DeWitt equation offers a glimpse into this realm. This equation attempts to describe the quantum state of the entire universe, but it lacks a time variable. In classical physics, time is a parameter that tracks change, but in the Wheeler-DeWitt framework, the universe is static with no temporal evolution. This suggests that time is not fundamental, but an emergent property, arising only when the universe reaches a certain scale or complexity. In the timeless state, reality is frozen in a superposition of all possible configurations, a snapshot of existence without progression. What does it mean for something to exist in such a state? Existence here is not about physical objects or events, but about abstract possibilities. Some theories propose that the timeless state is a realm of pure information or mathematical structures. For instance, the mathematical universe hypothesis, suggested by physicist Max Tegmark, posits that reality is fundamentally a set of mathematical relations. In the absence of time and space, these relations define a proto-reality, a network of possibilities that could give rise to a universe like ours when conditions allow. Another perspective comes from the study of quantum gravity, where space-time is not a continuous fabric, but a discrete, quantized structure. At the Planck scale, where quantum effects dominate, space-time may dissolve into a formless state, neither spatial nor temporal. Models like causal set theory propose that space-time emerges from a collection of discrete events, like points in a graph, with no inherent order or geometry. In the timeless state, these events exist in a disordered, pre-geometric form, waiting for a structure to emerge that we would recognize as space-time. The timeless state also raises questions about causality. In our universe, cause precedes effect, a sequence rooted in time's arrow. Without time, causality as we understand it cannot exist. Instead, the relationships between quantum states or events might be defined by correlations or patterns independent of temporal order. This idea is explored in theories like quantum causal histories, where the universe's structure is built from a web of probabilistic connections rather than a linear progression of events. How could our universe, with its familiar dimensions of time and space, emerge from such a state? One possibility is that the timeless state is inherently unstable, prone to transitioning into a structured reality. In quantum cosmology, this transition might occur through a process akin to quantum tunneling, where a wave function representing a timeless state evolves into one describing a universe with time and space. This tunneling event could mark the onset of the Big Bang, not as a creation from nothing but as a shift from a formless state to one with defined dimensions. The timeless state challenges our understanding of existence itself. While we cannot observe this state directly, its echoes linger in the universe's earliest moments, preserved in the cosmic microwave background or the distribution of galaxies, which hint at the quantum origins of space-time. Imagine a realm without depth, without the familiar expanse of stars and galaxies, where the universe's essence is encoded on a flat, ethereal surface. This is the holographic principle, a vision that suggests our three-dimensional world, with all its complexity, might be a projection of information stored in a two-dimensional realm. In the moments before the Big Bang, this principle offers a glimpse into a pre-universe where reality was not yet sculpted, but existed as a delicate tapestry of quantum information waiting to unfold. This enigmatic concept begins with a puzzle born from the study of black holes. Their event horizons, the invisible boundaries that trap light and matter, hold a secret, all the information about a black hole's contents. Every particle, every force, appears to be encoded on this two-dimensional surface, not within its three-dimensional core. Physicists Gerard Hooft and Leonard Susskind extended this idea to propose that the entire universe might be holographic. The three-dimensional reality we perceive, planets, stars, and the vastness of space could be a projection of data inscribed on a lower dimensional boundary, a cosmic blueprint that predates the Big Bang itself. In the pre-Big Bang state, this holographic surface is not a physical object, but an abstract construct, a two-dimensional field of quantum information. This field encodes the potential for everything that would become our universe, the arrangement of particles, the strength of forces, the geometry of space-time. Unlike the familiar world of depth and distance, this pre-universe exists without spatial dimensions as we understand them, a realm where information alone defines reality. The Big Bang, in this view, is not an explosion in space, but the moment when this encoded data began to project outward, weaving the three-dimensional cosmos we inhabit. The holographic principle finds rigorous grounding in the anti-de Sitter correspondence, a breakthrough from string theory introduced by Juan Maldacena in 1997. This framework describes a universe with a negatively curved geometry known as anti-de Sitter space, which is mathematically equivalent to a conformal field theory on its boundary. The CFT, a quantum theory without gravity, lives in one fewer dimension than the anti-de Sitter space it describes. This duality suggests that a lower dimensional quantum system can fully encode a higher dimensional universe, including gravity. For the pre-Big Bang state, this implies that a two-dimensional quantum field could contain the blueprint for our three-dimensional reality, with the Big Bang marking the transition from information to physical structure. This idea is supported by precise mathematical mappings. In anti-de Sitter space, every event, particle, or gravitational effect in the three-dimensional universe corresponds to a specific configuration in the two-dimensional boundary theory. For example, the motion of particles in the bulk is mirrored by changes in the quantum states on the surface. In the pre-universe, this boundary could be a timeless, spaceless quantum system where the rules of physics are encoded as correlations between quantum states. When the universe emerged, These correlations translated into the familiar dimensions of space and time, with gravity arising as an emergent property of the boundary's quantum dynamics. The holographic pre-universe also draws from black hole thermodynamics, particularly the Bekenstein-Hawking entropy. Jacob Bekenstein showed that a black hole's entropy, a measure of its information content, is proportional to the area of its event horizon, not its volume. This area law suggests that information scales with a two-dimensional surface, not a three-dimensional space. For the pre-universe, this implies that the information needed to describe the cosmos was stored on a flat boundary, with the Big Bang acting as the process that projected this information into a three-dimensional reality. The entropy of this boundary sets a limit on the universe's complexity, ensuring that all its contents, galaxies, stars, and planets fit within the data encoded on the surface. One model exploring this idea is the holographic cosmology proposed by Paul McFadden and Kostas Skinderis. Their work suggests that the early universe, during its inflationary phase, can be described by a two-dimensional conformal field theory. The fluctuations in this field correspond to the density variations observed in the cosmic microwave background, the relic radiation from the Big Bang. These variations, which seeded the formation of galaxies, are consistent with a holographic origin, where quantum fluctuations on a boundary surface translate into the large-scale structure of the universe. The holographic principle also connects to quantum information theory. In this view, the pre-universe's boundary is a quantum system where information is stored in qubits, the basic units of quantum data. These qubits encode the potential states of the universe, from particle interactions to gravitational fields. As the universe emerged, these qubits gave rise to spacetime itself, with geometry and matter arising from their entanglement patterns. This perspective aligns with ideas like the it from bit hypothesis proposed by John Wheeler, which posits that all physical reality is fundamentally information-based. The holographic pre-universe is not directly observable, as it exists beyond the reach of our instruments. However, its predictions leave traces in the cosmos. The cosmic microwave background's power spectrum, the distribution of its temperature fluctuations, matches the patterns expected from a holographic model. These fluctuations, stretched by inflation, reflect the quantum correlations of the pre-universe's boundary, offering indirect evidence of its two-dimensional origins. Additionally, experiments probing quantum gravity, such as those studying gravitational waves or high-energy particle collisions, may one day provide clues about the holographic nature of reality. This principle redefines the pre-Big Bang state as a realm of pure information, where the universe's potential is encoded in a flat quantum landscape. The three-dimensional world we experience, with its vast galaxies and intricate laws, is a projection of this deeper reality, like a hologram springing from a film. The Big Bang, rather than a creation from nothing, becomes a translation of information into physical form, a moment when a two-dimensional blueprint unfolded into the cosmos we know. Imagine a universe where the world we know, length, width, height, and time, is only part of the story. Beyond these familiar dimensions lie others, hidden from view, folded into spaces so small they defy imagination. String theory, a bold framework in modern physics, suggests that these extra dimensions existed before the Big Bang, shaping a reality where time and space were yet to form. This theory, replaces particles with tiny, vibrating strings and introduces intricate geometries, offering a window into the universe's earliest moments. String theory redefines the building blocks of reality. Instead of point-like particles, such as electrons or quarks, it proposes one-dimensional strings, smaller than just 10 to the minus 35 meters, vibrating at different frequencies. Each vibration mode corresponds to a specific particle or force, electrons, photons, or even gravitons, the carriers of gravity. Unlike standard physics, which operates in 4 dimensions, 3 spatial plus time, string theory requires 10 or 11 dimensions to be mathematically consistent. The extra dimensions, too small to detect, are curled up into compact structures, invisible yet essential to the theory's framework. Before the Big Bang, these extra dimensions could have defined the universe's state. In this pre-cosmic era, all dimensions, visible and hidden, might have been compressed to the Planck scale, around just 10 to the minus 35 meters. Here, strings and higher dimensional objects called branes interacted in a dense, multidimensional environment. Branes, short for membranes, are surfaces that can exist in various dimensions: a one-dimensional string, a two-dimensional sheet, or higher dimensional structures. These branes, vibrating with stringy energy, could have shaped the conditions that led to the universe's expansion. The extra dimensions are not simple shapes, but complex geometries known as Calabi-Yau manifolds. These manifolds, smaller than 1033 meters, are intricate, multi-dimensional structures with hundreds of interconnected holes, curves, and folds. Each Calabi-Yau shape determines how strings vibrate within it, which in turn defines the particles and forces that emerge. For example, the number and arrangement of holes in a manifold influence the types of particles possible, from quarks to photons, and the strength of fundamental forces like electromagnetism or gravity. In the pre-Big Bang state, the specific configuration of these manifolds could have set the rules for the physics that would govern the emerging universe. String theory's pre-Big Bang scenario envisions a highly compact universe where all dimensions were squeezed together. In this state, strings vibrated within the curled-up dimensions, their interactions governed by quantum mechanics. The energy from these vibrations could have triggered a rapid expansion, unfolding the 3 spatial dimensions we observe while keeping the extra ones compact. This process, driven by the dynamics of strings and branes, might have marked the transition to the Big Bang, transforming a multidimensional reality into the 4-dimensional spacetime we experience. Another model within string theory involves branes as the drivers of cosmic origins. In M theory, a broader framework that unifies different versions of string theory, our universe might exist on a 3-dimensional brane, a kind of cosmic sheet floating in a higher dimensional space called the bulk. Before the Big Bang, 2 branes, each carrying strings and energy, could have moved through this bulk. Their collision would release immense energy, initiating the rapid expansion that became the Big Bang. This collision model, known as the brane world scenario, suggests that the universe's birth was a dynamic event in a multidimensional landscape. Supersymmetry, a key feature of string theory, could have played a role in this pre-universe. Supersymmetry proposes that every particle has a heavier partner, creating a balance that stabilizes the extra dimensions. In the pre-Big Bang state, this symmetry might have kept the extra dimensions curled up, allowing only the familiar 3 spatial dimensions to expand. The specific shape and size of the Calabi-Yau manifolds, influenced by supersymmetry, would determine the constants of nature, such as the strength of gravity, or the mass of particles shaping the physics of the emerging cosmos. The extra dimensions also explain why gravity appears weaker than other forces. In string theory, gravity, carried by gravitons, can propagate through the extra dimensions, while other forces, like electromagnetism, are confined to our three-dimensional brain. In the pre-universe, this ability of gravity to interact with the hidden dimensions could have influenced the dynamics of brains and strings, guiding the transition from a compact, multidimensional state to an expanding universe. The leakage of gravity into the bulk might have set the initial conditions for the Big Bang's explosive growth. String theory's mathematical structure provides a consistent way to describe this pre-Big Bang state. Unlike general relativity, which fails at singularities, string theory avoids infinite densities by treating space-time as a product of string vibrations. The equations governing strings and brains remain well-defined even at the Planck scale, offering a framework where quantum mechanics and gravity coexist. For instance, the theory's T-duality shows that a universe with tiny dimensions is equivalent to one with large dimensions, suggesting that the pre-Big Bang state could have been a mirror of an expanding cosmos. While direct evidence for extra dimensions remains elusive, experiments offer indirect clues. The Large Hadron Collider searches for supersymmetric particles or anomalies in particle interactions that might hint at hidden dimensions. These experiments probe energies far below the Planck scale, but they constrain the possible sizes of extra dimensions, typically less than 10 to the power minus 18 meters. Cosmological observations, like the cosmic microwave background, also provide insights. The patterns of temperature fluctuations in this radiation, shaped by the early universe's physics, could reflect the influence of multidimensional geometries, aligning with predictions from string theory models. String theory's extra dimensions are not arbitrary, but mathematically necessary. The theory's consistency requires 10 dimensions for superstring theory, or 11 for M theory, with the extra dimensions compactified into Calabi-Yau manifolds. These manifolds come in thousands of possible configurations, each corresponding to a different set of physical laws. In the pre-Big Bang state, the choice of manifold would determine the universe's properties, from the number of particle types to the strength of fundamental forces, setting the stage for the cosmos we observe. The role of brains extends beyond collisions. In some models, our universe's brain could have been embedded in a higher dimensional bulk filled with other brains, each with its own strings and physics. The interactions between these brains, mediated by strings, could have created fluctuations that triggered the expansion of our three-dimensional brain. This dynamic interplay, governed by the rules of M theory, paints a picture of a pre-universe where multidimensional structures shape the conditions for cosmic birth. Picture a universe that never truly begins, but instead transforms, cycling through phases of collapse and rebirth. Loop quantum gravity, a theory aiming to merge quantum mechanics with gravity, proposes that the Big Bang was not the start of everything, but a dramatic transition, a cosmic bounce from a previous universe. This idea, rooted in the quantization of spacetime itself, suggests a reality where singularities vanish, replaced by a quantum bridge connecting one cosmos to another. Loop quantum gravity reimagines spacetime not as a smooth, continuous fabric, as in general relativity, but as a discrete network of tiny loops, roughly 10 to the power minus 35 meters in size, the Planck length. These loops, often described as the atoms of spacetime, form a granular structure called a spin network. Each node and link in this network carries quantum properties like area and volume in discrete packets, much like energy levels in an atom. In the pre-Big Bang era, this quantized structure could have governed the universe's behavior, preventing the infinite densities predicted by classical physics. In general relativity, the Big Bang begins with a singularity, a point of infinite density and temperature where space-time collapses and equations fail. Loop quantum gravity challenges this view by introducing quantum effects that smooth out such singularities. At the Planck scale, the granular nature of spacetime creates a repulsive force known as quantum gravity corrections that halts the collapse of a contracting universe. Instead of crunching into a singularity, the universe reaches a maximum density, around 10 to the power 94 grams per cubic centimeter, and rebounds, expanding into what we call the Big Bang. This bounce hypothesis suggests that our universe emerged from the ashes of a prior one, linked by a quantum transition. The mathematics of loop quantum gravity relies on spin networks and their evolution over time, described by spin foam models. A spin network is a graph where nodes represent quanta of volume and edges represent quanta of area, connected in a way that encodes the geometry of spacetime. In the pre-Big Bang phase, the universe might have been a highly compressed spin network, its geometry defined by these quantum loops. As the universe contracted, the density increased until quantum effects kicked in, transforming the collapse into an expansion. The spin foam, a four-dimensional structure, describes this transition, mapping how the network evolves from a contracting to an expanding state. The bounce hypothesis is formalized in loop quantum cosmology, a simplified version of loop quantum gravity applied to the universe as a whole. Contracting universe, shrinking toward a big crunch, undergoes a smooth bounce at the Planck scale, expanding into a new universe with properties like ours. The bounce scenario requires a universe that was contracting before the Big Bang. This prior universe could have been similar to ours, with stars, galaxies, and its own laws of physics, gradually collapsing under gravity. As it approached a Planck density, quantum gravity effects reversed the collapse, triggering rapid expansion. The bounce preserves some features of the prior universe, such as its entropy or large-scale geometry, but resets others, like the distribution of matter, through quantum fluctuations amplified during the bounce. One key prediction of loop quantum cosmology is the duration of the bounce. Unlike the instantaneous singularity of general relativity, the bounce occurs over a finite time, roughly 10 to the power minus 43 seconds, the Planck time. During this period, the universe transitions from contraction to expansion, with quantum fluctuations shaping the initial conditions of the new cosmos. These fluctuations, stretched by subsequent inflation, leave imprints in the cosmic microwave background, the faint radiation from the early universe. Observations of the CMB's power spectrum, the pattern of its temperature fluctuations, could reveal signatures of the bounce, such as subtle deviations from classical predictions. Loop quantum gravity, quantized spacetime, also affects the behavior of gravity at extreme scales. In classical gravity, a collapsing universe becomes infinitely dense, but in loop quantum gravity, the discrete nature of spacetime imposes a limit. The loops in the spin network cannot be compressed beyond a certain point, creating a repulsive force that drives the bounce. This is described by the Ashtekar variables, a reformulation of Einstein's equations in loop quantum gravity, which treats spacetime as a quantum field. These variables allow physicists to calculate the dynamics of the bounce, showing how the universe transitions without encountering a singularity. The bounce hypothesis also explores the role of quantum geometry. In loop quantum gravity, geometry is not a fixed backdrop, but a dynamic entity, evolving through quantum states.
Before the Big Bang, space may have been a compact spin network, Jess, made of tiny nodes and links. As the universe shrank, quanta grew dense. Then came the bounce show, a reorganization that became space-time.
Numerical models in loop quantum cosmology provide detailed predictions about the bounce. These models also predict that the bounce is symmetric, meaning the contracting and expanding phases mirror each other in certain properties, like the total energy. However, quantum fluctuations introduce randomness, ensuring that the new universe differs from its predecessor in subtle ways, such as the distribution of galaxies. The bounce hypothesis also connects to the concept of entropy. In a contracting universe, entropy, the measure of disorder, increases as stars form and galaxies merge. During the bounce, quantum effects might reset or redistribute entropy, allowing the new universe to start with a low entropy state, consistent with the second law of thermodynamics. This reset could explain why our universe began in a highly ordered state, as evidenced by the uniformity of the CMB. While direct observation of the pre-Big Bang universe is impossible, loop quantum cosmology offers testable predictions. The CMB's temperature fluctuations, measured by satellites like Planck, could show anomalies such as non-Gaussian patterns or suppressed power at large scales that hint at a bounce. Gravitational wave experiments, like LIGO, might detect echoes of the bounce in the form of primordial gravitational waves, though these signals would be faint. Future observatories, such as the Square Kilometre Array, could probe the early universe's structure, offering further clues about loop quantum cosmology's predictions. Loop quantum gravity framework relies on rigorous mathematics, including the use of Ashtekar-Barbero connections and holonomies, quantities that describe the curvature and topology of space-time. These tools allow physicists to model the universe's evolution at the Planck scale, where classical gravity fails. The theory also draws on canonical quantization, treating space-time as a quantum system with discrete states, unlike the continuous space-time of general relativity. Imagine a cosmos born not from a single explosive point, but from a monumental collision of vast invisible surfaces floating in a higher dimensional realm. The Ekpyrotic Universe model, rooted in M-theory, proposes that our universe emerged from the clash of two higher dimensional branes, reshaping the idea of the Big Bang into a dynamic encounter. This theory, blending string theory's extra dimensions with cosmological evolution, offers a precise framework for the universe's origin, where the pre-Big Bang state is a multidimensional dance of branes and strings. The Ekpyrotic model, introduced in 2001 by physicists Paul Steinhardt, Justin Curry, Berta Vrutt, and Neil Turok, draws from M-theory, an extension of string theory that unifies its various forms. M-theory operates in 11 dimensions, 10 spatial and 1 temporal, and describes the universe's fundamental constituents as strings and branes. Branes, short for membranes, are multidimensional surfaces that can range from one-dimensional strings to higher dimensional objects. In the Ekpyrotic scenario, our universe exists on a three-dimensional brane, a cosmic sheet within a higher dimensional space called the bulk. Before the Big Bang, two such branes, each with its own physics and strings, floated in this bulk, separated by a tiny distance, possibly as small as 10 to the minus 30 meters. These branes were not static, but dynamic, moving slowly toward each other due to a weak attractive force mediated by the exchange of strings or gravitons. The Ekpyrotic model posits that their collision released immense energy, triggering the rapid expansion we associate with the Big Bang. This collision, rather than a singularity, marks the birth of our universe, transforming a multidimensional interaction into the hot, dense cosmos we observe. The term ekpyrotic comes from the Greek word for conflagration, evoking the fiery energy of this collision. Unlike the standard Big Bang model, which starts with a point of infinite density, the Ekpyrotic scenario avoids singularities by distributing the energy across the brane's surfaces. The collision occurs over a finite region, governed by the physics of M-theory, where the extra dimensions, curled up into tiny calibi, Yau manifolds, play a critical role. These manifolds, complex geometries smaller than 10 to the minus 33 meters, define the properties of strings and the forces within each brane, shaping the physics of the emerging universe. In the pre-Big Bang state, the bulk is a higher dimensional space, possibly five-dimensional, where the two branes reside. One brane might represent our universe, while the other is a parallel brane with its own matter and forces. The branes are separated along an extra-spatial dimension, and their motion is governed by a potential energy described by M-theory's equations. This potential, often modeled as a scalar field, drives the branes toward each other, with the collision releasing energy equivalent to temperatures of about 10 quintillion giga-electron-volt, sufficient to initiate cosmic expansion. The Ekpyrotic model replaces the rapid inflation of standard cosmology with a slow contraction phase before the collision. During this phase, the branes approach each other over billions of years, their separation shrinking gradually. The contraction flattens the branes, making them nearly uniform, which explains the smoothness of our universe without requiring inflation. As the branes collide, their kinetic energy converts into heat and matter, creating a hot, dense state akin to the Big Bang. This process, described by the Friedmann equations modified for brane dynamics, ensures that the universe emerges with the right conditions for stars and galaxies to form. Quantum fluctuations play a key role in this model. As the branes approach, quantum ripples in the scalar field, governing their motion, create tiny variations in their surfaces. These variations, amplified during the collision, become density fluctuations in the new universe, seeding the formation of galaxies. Unlike inflationary models, where fluctuations arise from a quantum field stretched by rapid expansion, the ekpyrotic fluctuations are generated by the brane's slow convergence, producing a distinct pattern in the cosmic microwave background. This pattern, characterized by a flatter power spectrum at large scales, could distinguish the ekpyrotic model from inflation in future observations. The mathematics of the ekpyrotic scenario relies on M-theory's framework, particularly the low energy limit described by 11-dimensional supergravity. The branes are modeled as solutions to supergravity equations, with their dynamics governed by the Dirac-Born-Infeld action, which describes how branes move and interact in the bulk. The collision is not a violent crash, but a smooth merging, where the brain's energy is transferred into particles and radiation. This process avoids the singularities of classical cosmology, as the extra dimensions provide additional degrees of freedom that regularize the physics. The Ekpyrotic model also incorporates the concept of the cyclic universe, a variant where the brain's collision is not a one-time event, but part of a repeating cycle. After the collision, the brains bounce apart and the universe expands, cools, and eventually contracts again, driven by the same scalar field. This cyclic model suggests that our Big Bang was one of many, each cycle producing a new universe. The cycle's duration could span trillions of years, with each phase leaving subtle imprints in the CMB, such as low-frequency gravitational waves, which future observatories like the Simons Observatory might detect. The extra dimensions in M-theory are crucial to the Ekpyrotic model. The bulk's geometry, often modeled as an orbifold with the brains at its boundaries, constrains the brain's motion. The Calabi-Yau manifolds embedded in the brains determine the types of particles and forces, with their shapes defined by hundreds of parameters, fixing the constants of physics like the electron's mass or the strength of gravity. The collision's energy depends on the brain's separation and the bulk's properties, calculated using M-theory's effective field theory. Observational tests for the Ekpyrotic model focus on the CMB and gravitational waves. The model predicts a nearly scale invariant spectrum of density fluctuations, similar to inflation, but with distinct features, such as a slight tilt in the scalar, spectral index measurable by experiments like Planck or the upcoming Litbird satellite. Unlike inflation, the Ekpyrotic scenario produces fewer primordial gravitational waves, as the slow contraction suppresses tensor modes. Detecting these differences in the CMB's polarization patterns could provide evidence for the model. The Ekpyrotic universe relies on precise mathematical tools, including the Randall-Sundrum model, which describes brains in a warped extra dimension, and the anti-de Sitter correspondence, which connects brain dynamics to quantum field theories. These frameworks ensure that the collision is consistent with quantum gravity, avoiding the infinities that plague classical singularities. The model also draws on string theory's T-duality, which relates small and large dimensions, suggesting that the pre-Big Bang state could mirror the expanding universe in a dual description. The Ekpyrotic scenario paints a vivid picture of a pre-Big Bang state, where two brains, vibrating with strings in a multidimensional bulk, slowly converged. Their collision, a cosmic spark in a higher dimensional realm, unleashed the energy that became our universe, with quantum fluctuations shaping its structure. What if the universe began from nothing, not an empty void, but a restless quantum vacuum buzzing with fleeting activity? The vacuum genesis hypothesis, rooted in quantum field theory, suggests that our cosmos emerged from a quantum fluctuation in a vacuum state where virtual particles and zero-point energy sparked the Big Bang. This idea explores a pre-universe defined by the subtle probabilistic dance of quantum fields, where the boundary between nothing and something fades. Quantum field theory views the vacuum as a dynamic sea of quantum fields, not an empty space. Every particle, electrons, quarks, photons, corresponds to a field that fills all space. Even in a vacuum, these fields are active, driven by the Heisenberg uncertainty principle, which allows energy to fluctuate briefly. These fluctuations create virtual particles, pairs of particles and antiparticles that appear and vanish almost instantly, borrowing energy from the vacuum for less than 10 to the power minus 21 seconds. In the pre-Big Bang era, this quantum vacuum could have been the universe's foundation. The vacuum genesis hypothesis proposes that a rare, large fluctuation in these fields produced a bubble of energy dense enough to trigger rapid expansion, becoming the hot, dense state of the Big Bang. This fluctuation, occurring at the Planck scale, 10 to the power minus 35 meters and 10 to the power minus 43 seconds, involved energies around 10 to the power 19 giga electron volts, enough to start cosmic evolution. This process, called vacuum fluctuation or quantum nucleation, relies on the probabilistic nature of quantum mechanics, where even a vacuum can produce something from seemingly nothing. Virtual particles are key to this scenario. Unlike real particles, they exist temporarily, governed by the uncertainty principle's energy-time relation, written as delta E times delta T greater than or equal to h bar over 2, where h bar is the reduced Planck constant. In the vacuum, pairs like electrons and positrons appear and annihilate quickly to repay the borrowed energy. In the pre-universe, a fluctuation with a larger energy spike could have persisted, stabilized by specific field configurations, such as a scalar field with a high energy state. This field, often called the inflaton in related models, could drive exponential expansion, turning the fluctuation into a universe. 0-point energy, the minimum energy of quantum fields in their lowest state, fuels these fluctuations. In quantum field theory, each field mode, corresponding to different frequencies, contributes energy proportional to h bar times omega over 2, where omega is the frequency. Summing over all modes, the vacuum's energy density is theoretically infinite, but a cutoff at the Planck scale gives a finite value, about 10 to the power 113 joules per cubic meter. In the pre-Big Bang vacuum, this energy could provide the raw material for a fluctuation to ignite the cosmos. The vacuum genesis model uses quantum cosmology, describing the universe's wave function with equations like the Wheeler-DeWitt equation. This equation, lacking a time variable, portrays the pre-universe as a static quantum state, a superposition of possible configurations. A vacuum fluctuation could shift this state, tunneling from a high-energy vacuum to a lower energy state with expanding spacetime. This tunneling, calculated using path integral methods, has a probability governed by the action, typically e to the power minus se, where s is the Euclidean action, making it rare but possible. The geometry of this process involves instantons, solutions to quantum field equations that describe tunneling events. In the pre-Big Bang vacuum, an instantine represents a bubble of true vacuum, a region with lower energy emerging within a false vacuum, a metastable high-energy state. The bubble's size, roughly the Planck length, and its energy, set by the field's potential, allow it to expand rapidly if the potential shape permits. This expansion, described by the Coleman-de Lucia formalism, matches the Big Bang's conditions, producing a hot, dense universe. The vacuum's properties are shaped by the Higgs field, which gives particles mass through its vacuum expectation value, about 246 giga electron volts. In the pre-universe, the Higgs field, along with other scalar fields, could have existed in a false vacuum state with high potential energy. A quantum fluctuation could push the field over this energy peak, causing a phase transition where the vacuum decays, releasing energy that drives cosmic expansion. The cosmic microwave background or CMB, offers clues for vacuum genesis. Its temperature fluctuations, measured by satellites like Planck, reflect quantum fluctuations from the early universe. In this model, these fluctuations come from the vacuum's quantum noise, amplified during the rapid expansion after the fluctuation. The power spectrum of these fluctuations, with a scalar spectral index near 0.96, matches observations, supporting the idea that a vacuum fluctuation could seed cosmic structure. The model predicts a low level of primordial gravitational waves, as the vacuum fluctuation produces mainly scalar perturbations. Experiments like BICEP-3 or the upcoming Simons Observatory aim to detect these waves through CMB polarization, testing the model. A low tensor to scalar ratio, below 0.1, would align with vacuum genesis, distinguishing it from some inflationary models with stronger gravitational wave signals. Quantum field theory's renormalization techniques handle the vacuum's infinite energy problem. By setting an energy cutoff at the Planck scale, physicists calculate a finite vacuum energy density, though its exact value is uncertain due to the cosmological constant problem. The observed vacuum energy is 10 to the power 120 times smaller than predicted. In the pre-Big Bang state, a dynamical mechanism, like a decaying false vacuum, might adjust the energy to match the universe's expansion rate. The vacuum genesis hypothesis also ties to eternal inflation, where our universe is one of many bubbles nucleating in a larger multiverse. Each bubble arises from a vacuum fluctuation, with different bubbles having distinct physical constants based on their field configurations. String theory suggests a landscape of 10 to the power 500 possible vacua, each corresponding to a different universe. In the pre-Big Bang state, our universe's vacuum could have been one such configuration, selected by a rare fluctuation that allowed expansion. Virtual particles extend to quantum electrodynamics and quantum chromodynamics, describing electromagnetic and strong nuclear forces. In the vacuum, virtual photons and gluons contribute to the energy, creating complex interactions. In the pre-universe, these could stabilize a fluctuation, allowing it to grow into a universe. The Casimir effect, where vacuum energy causes plates to attract in a lab, provides experimental evidence for virtual particles, supporting their role in cosmic origins. The model uses precise mathematical tools, like Feynman diagrams, to calculate fluctuation probabilities and effective field theories for scalar field dynamics. The Hartle-Hawking wave function, an alternative to Wheeler-DeWitt, describes the universe's quantum state with a finite probability of nucleating from a vacuum. These frameworks ensure consistency with quantum mechanics and gravity, offering a rigorous view of the pre-Big Bang vacuum. In this scenario, the pre-universe is a quantum vacuum, alive with virtual particles and zero-point energy, where a rare fluctuation sparked the cosmos. The Big Bang becomes a transition from a high-energy vacuum to an expanding universe, driven by the probabilistic nature of quantum fields, grounded in the mathematics of quantum field theory. Quantum entanglement, a phenomenon where particles share special connections across vast distances, might hold clues to the universe's origins. The idea that entanglement could predate space itself suggests that the pre-Big Bang state was a web of quantum correlations, with space-time emerging from these links. This concept, grounded in quantum information theory and quantum gravity, explores a pre-universe where the fabric of reality was woven from the intricate ties of entangled quantum states. In quantum mechanics, entanglement occurs when two or more particles become linked, so that measuring one instantly affects the other, regardless of distance. This correlation, described by a shared quantum state, defies classical notions of locality. In the pre-Big Bang era, before space and time, as we know them existed, quantum entanglement could have defined a proto-reality, a network of quantum states without a spatial or temporal framework. This network might have served as the foundation from which space-time emerged, with entanglement shaping the universe's structure. The concept builds on quantum information theory, which treats information as a fundamental aspect of reality. In this view, the pre-universe is a collection of quantum bits, or qubits, each representing a basic unit of information. These qubits, entangled in complex patterns, encode the potential for particles, forces, and geometry. The density matrix, a mathematical tool describing quantum states, quantifies these correlations with entanglement entropy, measuring the strength of connections between subsystems. In the pre-Big Bang state, this entropy could have been maximal, indicating a highly entangled pre-geometric system. One important idea is called ER equals EPR, suggested in 2013. It connects two things, quantum entanglement and wormholes. The idea is that when particles are entangled, they might be linked by tiny wormholes, shortcuts in space. In the pre-universe, these links could have formed a web of connections even before space existed. This network might have laid the groundwork for space and time to appear. The idea that space-time comes from entanglement is also explored in theories like the holographic principle and tensor networks. In the holographic view, a flat, lower-dimensional system of entangled particles can create a higher dimensional space. For the early universe, this could mean that a simple boundary of entangled bits gave rise to full space-time. Tensor networks offer another way to picture this. They treat space as a grid of entangled states, where the layout of the network shapes things like distance and curves. Before the Big Bang, such a network could have acted as a blueprint for how space and time would form. The concept of quantum entanglement helps explain how the universe may have started. Before the Big Bang, everything could have been deeply connected in a highly entangled state, meaning that parts of the system were strongly linked, even across vast distances. This state had very high entropy or disorder. As space and time began to form, that quantum disorder may have become the heat and energy we see in the early universe, especially in the cosmic microwave background. The idea is that small-scale quantum links came together to shape the large-scale structure of space itself. One theory, called the anti-de Sitter correspondence, supports this idea. It suggests that a network of entangled quantum bits on a boundary, something with no space or time, can describe a full universe with gravity and space inside. In this view, the Big Bang could be the moment when this inner space appeared from pure quantum entanglement. The more entangled the system was, the more space it created, shaping the universe's geometry as it grew. Quantum entanglement also connects to the concept of quantum gravity. In loop quantum gravity, space-time is quantized into discrete loops, and entanglement between these loops could define their connectivity. In the pre-Big Bang state, a spin network, a graph of quantized space-time, might have been a web of entangled states with links representing entanglement rather than physical distance. The evolution of this network, described by spin foam models, could mark the transition to a classical spacetime, with entanglement providing the glue that holds the geometry together. The role of entanglement is further explored in the IT from bit hypothesis, proposed by John Wheeler, which posits that physical reality emerges from information. In the pre-universe, information encoded in entangled qubits could have defined the potential for space-time, matter, and forces. We don't have direct proof for this idea yet, but the evidence we do have is promising. Tiny temperature changes in the cosmic microwave background, measured by the Planck satellite, match what we'd expect if they came from early quantum fluctuations. In models based on entanglement, these fluctuations were already present before the Big Bang and got stretched out as the universe expanded. Some researchers think the overall disorder, or entropy, in the CMB also supports this view. It matches what certain theories predict if space came from quantum entanglement. Gravitational waves might offer more clues. These ripples in space, possibly created in the universe's earliest moments, could carry signs of quantum entanglement from before the Big Bang, such as unique patterns in how they move. Future space-based detectors like LISA could help find these patterns. So far, current observations also match predictions made by these entanglement-based models. The pre-universe's entangled state could also explain the universe's low initial entropy. In a highly entangled system, the quantum state appears disordered at the microscopic level, but ordered macroscopically as correlations align to form spacetime. This aligns with the second law of thermodynamics, where the universe's entropy increases post-Big Bang. The Penrose process, extracting energy from entangled states near black holes, suggests that entanglement could drive dynamic processes like the emergence of spacetime. The mathematics of tensor networks provides a concrete model. In Mera, layers of entangled qubits correspond to different scales of spacetime, with deeper layers representing finer structures. In the pre-universe, a Mera-like network could describe a timeless state where entanglement organizes into a geometry during the Big Bang. The network's renormalization group flow, governed by unitary transformations, mirrors the emergence of classical spacetime from quantum correlations. Entanglement also ties to quantum error correction codes used in quantum computing to protect information. In the pre-universe, spacetime could be a code, with entanglement ensuring robustness against quantum noise. The surface state correspondence, proposed by Miyagi and Takayanagi, suggests that each entangled state on a boundary corresponds to a specific spacetime region, supporting the idea that entanglement structures the cosmos. The pre-Big Bang state, in this view, is a network of entangled quantum states, described by a wave function or density matrix with high entanglement entropy. The Big Bang marks the moment when these correlations, governed by quantum information theory and quantum gravity, crystallized into spacetime, with geometry emerging from the patterns of entanglement. This framework, rooted in precise mathematical models, portrays a pre-universe where quantum connections laid the foundation for the cosmos. The no-boundary proposal, introduced by Stephen Hawking and James Hartle in 1983, offers a unique perspective on the universe's origins, suggesting that the Big Bang was not a sharp starting point, but a smooth transition described by a concept called imaginary time. This framework, rooted in quantum cosmology, reimagines the pre-Big Bang state as a timeless, finite geometry where the universe emerges without a singular beginning, using mathematical tools to describe a cosmos that is self-contained. In quantum mechanics, time is typically treated as a real number, measured in seconds, guiding the evolution of physical systems. The no-boundary proposal replaces this with imaginary time, a mathematical construct where time is treated as a complex number using the imaginary unit I, the square root of -1. This approach, borrowed from quantum field theory, transforms time into a dimension resembling space, allowing the universe's early state to be described without the infinities of a classical singularity. In imaginary time, the pre-Big Bang universe is modeled as a smooth, four-dimensional geometry, like the surface of a sphere, with no sharp edges or starting points. The Hartle-Hawking no-boundary proposal uses the path integral formalism, a cornerstone of quantum mechanics developed by Richard Feynman. In this method, the probability of a quantum system transitioning from one state to another is calculated by summing over all possible paths, each weighted by a factor e to the power I times c over h bar, where s is the action and h bar is the reduced Planck constant. For the universe, the path integral sums over all possible geometries and field configurations, describing the wave function of the universe, known as the Hartle-Hawking wave function. In the pre-Big Bang state, this wave function represents a superposition of possible universes, with imaginary time smoothing out singularities. In a different way of looking at time, called imaginary time, the universe's early shape can be thought of like the surface of a smooth, four-dimensional sphere. There's no sharp beginning or edge, just a rounded shape that transitions smoothly into what we know as real time, starting at the Big Bang. This idea removes the concept of a singular starting point, replacing it with a smooth, finite beginning. According to this view, the universe could have started in a simple, curved state that followed the E rules of Einstein's theory of gravity. This early shape, often compared to a kind of curved space, sets the stage for the universe to emerge with certain properties more likely than others, especially those that are smoother and more stable. A special kind of field, similar to the one used in inflation theory, helps drive the expansion of the universe. Before the Big Bang, this field was stuck in a high-energy state. Through a process like quantum tunneling, it moved into a lower energy state, which kicked off the rapid expansion we call the Big Bang. The geometry of the no-boundary state is described by a metric, d squared equals d tau squared plus a squared times d omega squared, where tau is imaginary time, a is the scale factor, and d omega squared is the metric of a three-sphere. At tau equals 0, the scale factor is minimal, around the Planck length, and increases as tau grows, transitioning to real time at the Big Bang. This geometry avoids the infinite density of a singularity, as the curvature remains finite, with a Ricci scalar on the order of 10 to the power 70 per meter squared. The no-boundary proposal also predicts specific features in the cosmic microwave background. Quantum fluctuations in the scalar field during the imaginary time phase generate density perturbations, amplified during the transition to real time. These perturbations, described by a power spectrum with a scalar spectral index near 0.96, match CMB observations from Planck, which measure temperature fluctuations of about 10 to the power -5 Kelvin. The model predicts a low level of primordial gravitational waves with a tensor to scalar ratio below 0.1, consistent with current limits from BICEP 3. The proposal incorporates quantum gravity effects through the Wheeler-DeWitt equation, which describes the universe's quantum state without a time variable. In the no-boundary framework, this equation is solved using a Euclidean path integral, yielding a wave function peaked around a smooth, finite geometry. The probability distribution, P equals the absolute value of psi squared, favors universes with low initial entropy, explaining the observed order of the early universe, with an entropy of about 10 to the power 88 Boltzmann constants in the CMB. The role of imaginary time extends to quantum field theory's Wick rotation, a technique that transforms real-time t into imaginary time, tau equals I times t. This rotation simplifies calculations by converting oscillatory integrals into decaying exponentials, making the path integral convergent. In the pre-Big Bang state, Wick rotation creates a Euclidean geometry where the universe's wave function is dominated by a compact, boundary-free manifold. This manifold's topology, often a four-sphere, has a volume of about 10 to the power minus 105 cubic meters at the Planck scale. The no-boundary proposal also draws on the holographic principle, where the universe's information is encoded on a lower dimensional boundary. In imaginary time, this boundary is a three-sphere at the transition to real time, with an area of about 10 to the power minus 70 square meters. The entanglement entropy of this boundary, S equals A over 4 GeE, where A is the area and G is Newton's constant, matches the thermodynamic entropy of the emerging universe, supporting the model's consistency. Observational tests focus on the CMB and gravitational waves. The no-boundary model predicts a slightly red-tilted power spectrum with a spectral index n sub s equals 0.96 and minimal tensor perturbations detectable by future experiments like the Simmons Observatory or LIGHTBIRD. The model's prediction of low initial entropy aligns with the uniformity of the CMB, suggesting a smooth, ordered early universe. The mathematics of the no-boundary proposal uses saddle point approximations to evaluate the path integral, with the Euclidean action dominated by contributions from de Sitter-like geometries. The scalar field's potential, tuned to match the observed cosmological constant of 10 to the power minus 120 joules per cubic meter, ensures the universe expands at the right rate. The model also incorporates loop quantum gravity concepts, where space-time is quantized, supporting the idea of a finite, non-singular geometry. In the pre-Big Bang state, the no-boundary proposal describes a universe as a smooth, four-dimensional geometry in imaginary time, with a wave function encoding all possible configurations. The Big Bang marks the transition to real time, driven by quantum tunneling and scalar field dynamics, creating a cosmos with the properties we observe, grounded in the rigorous framework of quantum cosmology. The theories we've explored, quantum foam, timeless states, holographic boundaries, hidden dimensions, cosmic bounces, brane collisions, vacuum fluctuations, entangled networks, imaginary time, and chaotic epochs each tell a story of a cosmos born from something deeper than a simple beginning. They point to a reality where the question of before transcends science, touching the philosophical heart of existence. Why does the universe exist? Why do we, within it, ponder its origins? These questions, as timeless as the cosmos itself, linger beyond equations and observations. They invite us to wonder, to probe, to dream of a reality that may forever hold its secrets close. The mystery of what came before the Big Bang is not just about the past. It's about why there is anything at all, a riddle that binds us to the stars and the unknown beyond.